Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the question of the LRU cache. This is a very famous interview question. It's a very famous problem that really tests your knowledge of various data structures. The problem basically asks you to implement a class for an LRU cache. Now, what is an LRU cache? Well, LRU stands for least recently used. And so basically you're building a caching system that has all of the typical functionalities of a normal caching system. In other words, you can insert a bunch of key value pairs and store them in the cache. You can retrieve values by giving keys that are associated to those values in the cache. But then the LRU part of the cache comes into play when you're asked to retrieve the most recent key or the most recently accessed key. And similarly, if the cache reaches maximum capacity and you try to insert another key value pair in the cache that doesn't already exist in it, then the cache has to be able to evict or get rid of the least recently used or least recently accessed key value pair that it was storing. And so that is really where the tricky part of the algorithm or question comes into play. So in case that was unclear, let's dive into an example. I've got in front of me an LRU cache of size 3. And so we've already inserted a bunch of key value pairs. We've inserted the key value pair A mapping to 1, B mapping to 2, and C mapping to 3 in this order. So right now, the least recently used or accessed key and key value pair is going to be A1. And so right now, if we were to try to get the most recent key from this LRU cache, this is going to be a method that we're going to want to implement, get most recent key, it would be C, because C is the last key that we insert in the cache and that we accessed in general. Then if we were to call the get value from key method on this cache and we passed in the key A, then we would want to return the value 1 because A maps to 1, right? The value 1 is associated to the key A. And so what would happen at this point is A would become the most recently used or accessed key value pair. Or sorry, A1 would be the most recently used key value pair. A would be the most recent key. So if we accessed A1, we would then move A1 to the top of the LRU cache. We'd shift everything down, and A1 would now be the most recently accessed key, as I just said. Then, if we were to insert another key value pair, let's say that we wanted to insert D mapping to 4, right? What would happen is we would shift all of our values down, right? We would put D4 at the very top of the LRU cache because D4 would now be the most recent key value pair. But because our LRU cache has a maximum capacity or a maximum size, which is 3, right? And we already had 3 key value pairs in the cache, we would have to get rid of or evict the least recently used key value pair, which would be B mapping to 2 here. So we would grab B and just get rid of it, right? Dispose of it so we can erase it. And then lastly, if we were to try to access, right, the key value pair B2, so if we were saying, get value from key B, then we would want to return the null value or the none value because B is no longer in the cache. And then if we wanted to insert another key value pair with the key A, so if we wanted to insert A mapping to, let's say, 5, we would see that A is already in the cache, right? A already points to 1 in the cache. So even though our cache is at maximum capacity, all that we would do is erase our current A1 and replace it with A5, right? Because we would just overwrite the value. And then we would move that to the top of the cache because, or let me move it here, let me move this down, and we would move that to the top of the cache because it would now be the most recently sort of accessed value or key value pair. So that's how the LRU cache works. This is what we want to implement. How do we do this, right? One of the other specifications in the prompt is that we should be able to support all of these major functionalities in constant time. In other words, they should run in constant time. The time complexity of all of these sort of methods should be O of 1. So how do we do that? Well, the first thing that the majority of people are going to think about is a hash table, right? We want to access values that are stored at keys, right? We have these mappings of key value pairs, so it makes a lot of sense that we would have a hash table. Okay, so a hash table would definitely allow us to insert a new key. Let's say the Z mapping to 6. It would definitely allow us to store this or insert this new key value pair in constant time. If we wanted to access the value or this key value pair, and so we wanted to get the value from the key Z, that would also be pretty simple. We would just access the key Z in the hash table in O of 1 time. But then, how would we access the most recently used key, right? How would we get the most recent key? Similarly, how would we evict the least recently used key value pair when the time is needed, right? We would maybe store some kind of timestamp on every key value pair in the hash table, and then we'd have to iterate through all of the key value pairs in the hash table to find the most recent one by timestamp or the least recent one by timestamp. But that would be an O of n operation, right? We'd have to iterate through all the key value pairs. So maybe a hash table isn't the solution here. Okay, so let's see if we can come up with another data structure that might help us. What about an array, right? A list. You could store every key value pair in the list in order. In other words, like let's say we had a list right here. You could store, the first key value pair, let's say A mapping to 1. Then you could, have B mapping to 2. Whoops, I'm just going to write a few key value pairs here arbitrarily, C mapping to 3. And you could say at every point in time, let the value in the first position in the list be the most recent one. Let the value in the last position in the list be the least recent one. If we want to get the most recent key, we just access the array at index 0. If we want to evict the last key or the least recently used key, we can pop the final value out of the list. But then how do we get a value from a key, right? How do we know where a specific key value pair is in the array? We have to iterate through every value in the array. And similarly, how do we update a key value pair that's just been accessed to be the most recent one? Let's say that we wanted to access B mapping to 2 here, and then we wanted to make B2 the most recently used key value pair. We would have to, grab it, move it all the way to the front of the array, and then shift every other key value pair in the array, one position to the right, and then move it like this. That would be an O of n operation, right? Not only to find where the key value pair that we're trying to retrieve is, but then to move it to the start of the list, and then to shift every other key value pair down. That would be an O of n operation. So again, it doesn't look like an array or a list is great for what we want to do. So let's remove it. Okay, what about a linked list? So a linked list, I'll write it in green here this time. Again, we could have a bunch of arbitrary key value pairs, and I'll put them in parentheses to show that these are key value pairs. And, we could have a doubly linked list. If you're not familiar with doubly linked lists, I definitely encourage you to check out our doubly linked list construction question right here on algoexpert.io, because I'll assume that you know what it is here. So we could have a doubly linked list that has a bunch of nodes with key value pairs. And so how would this fare? Well, if we wanted to access the most recent key value pairs, we could make sure that the head of the doubly linked list could at all times carry the most recently used key value pair. So we could access it in O of 1 time by just accessing the head of the linked list. We could have the tail of the linked list always store the least recently used key value pair. And once again, if we wanted to evict that least recently used key value pair, we could just remove the tail of the linked list, right? So we would grab it, remove it, and make the previous value the new tail, and that would be O of 1 time also. Then this would actually be better than an array, because if we ever, let's say we were to access the key value pair B2, and we wanted to make B2 become the new most recent key value pair, we could just very simply move it without having to shift every other node. We could just move it, make it the head, right? So we would add a couple of pointers here, and then we could just erase these pointers here and connect them together like this. And this would be an O of 1 operation, right? To move a node in the linked list all the way to the head of the linked list, that would be an O of 1 operation, unlike in an array. But, so while all of this would be as good or better than an array, we would still have the same sort of pitfall, which is, how do we find a specific key value pair? If I tell you here in this linked list that has B2 as the head, C3 as the tail, and A1 in the middle, if I tell you, get me the value from the key A, how do I find that? I have to iterate through every node in the linked list to find the node that has a key that is equal to A, and then I find its value. But I have to iterate through all of the nodes. So once again, we're almost there, right? But we can't satisfy this condition of having all of the functionality run in O of 1 time. So at this point, if you were in an interview and you had thought about all of these data structures, you might be starting to panic. I can't find a data structure that will do everything for me. So that's when you have to realize that maybe you can combine data structures together. Not necessarily combine them into some sort of mega data structure, but rather use multiple data structures together in harmony and see if that can help you. So let me move our example LRU cache here to the top. We probably won't need that one anymore. But let's imagine that we had both a hash table and a linked list. Why am I picking those two data structures? Well, clearly the hash table was a must to give us that O of 1 access to a key value pair. Right? If I tell you get the value from the key A, it seems as though the only data structure that will allow you to do that in O of 1 time is going to be a hash table. And then every other functionality of the LRU cache seemed to be satisfied by the linked list. So what if we combined the two and had a hash table that maps to nodes in a doubly linked list? So let's see what that would look like. Imagine we had our LRU cache from the very beginning, where we had A pointing to 1, B mapping to 2, and C mapping to 3. So we're going to have A pointing to 1, B pointing to 2, and C pointing to 3. Let's rewrite this 3. And these are added in this order. So A1 was the first one, B2 was the second, and C3 was the third. A, B, and C are properties in a hash table. So I'll even write it here. I'll say this is a hash table. But then, instead of having A, B, and C map to their values, 1, 2, and 3, why don't we have them map to nodes in a doubly linked list? So let's rewrite this and say we'll have a node here that is going to be, A pointing to 1, B pointing to 2, and then here C pointing to 3, right? And these nodes are going to point to each other as they would in a doubly linked list. And so here in this case, we would have the tail of the doubly linked list would be here at the bottom, and the head of the doubly linked list would be here at the top because, remember, we added A1 at the very beginning, and then we added B2 and then C3. So C3 is the most recent key or key value pair. So it's going to be the head of the doubly linked list, and A1 is going to be the tail. So how does this help us, right? Well, let's think about it. When we want to insert a new key value pair, right? How do we do that? Well, first we check if the key that we're adding from the new key value pair that we're adding is in the cache, and our cache is represented by our hash table. So I guess I'll write here, this is our cache. So we check, let's say we want to add a new key, we'll call it D4, or new key value pair, D mapping to 4. And of course, we have to specify a maximum capacity for our cache. So we'll say it has a capacity of 3. So if we want to add D4, well, the first thing that we do is we check in our cache, which is represented by a hash table, if D already exists. If it doesn't exist, right, then we check what the current size of our cache is. If our current size is not the maximum capacity, so let's actually assume that this is a capacity of 4, because I want to go through this example. If our current size of our cache is not the maximum capacity, then all that we have to do is increment our current size. So let's say our current size was 3 right now. We would increment it to 4. And then we would say, go in our cache, and add in our hash table at the key D, a new node, a new doubly linked list node that stores both a key and a value, a key of D and a value of 4. So we're going to add here, I'll write it in green, we're going to add in our hash table a property D that is going to map to a new doubly linked list node that is going to have a key of D mapping to a value of 4. Okay? And now we're not done. The last thing that we want to do is, once we've added this value or this key value pair in our cache or in our hash table, we want to update it to be our most recent key value pair, because that's kind of the definition of the LRU cache, right? When you add a new key value pair, it becomes the most recent key value pair. So how do we do that? Well, we just grab this new or we don't even grab the mapping from our hash table to our doubly linked list node, right? All we do is we grab our doubly linked list node and we set it to be the head of our doubly linked list. So how's that going to work? Well, in code, obviously, we'd need some kind of doubly linked list class. But here, all we're going to do is grab our doubly linked list node and make it the head of our doubly linked list. And so I'll move this here, and I'll add pointers here between our new head and the previous head. Again, if you're familiar with doubly linked lists, making this new node the head of our doubly linked list is going to be an O of 1 operation, right? You're just kind of moving pointers around. That's it. And so in our hash table, our value or property D is now going to actually look something like this, right? The pointer, which was pointing to the node, which was here like a second ago, now it's going to look something like, the arrow is going to go all the way to here, right? The property in the hash table like doesn't move, right? Because it's just there, but it just points to the same node, but that is now positioned at the head of the linked list. And of course, to make this clear in our example, we don't have to do this weird gigantic arrow. We can just move our letter D here and to point to the new head of the linked list. And so as you can see right now, we've inserted a new key value pair and made it the most recent key value pair in constant time. So now if I tell you, well, get me the most recent key value pair, all you're going to have to do is check our doubly linked list, check the head of the doubly linked list, and boom, you've got the key value pair D mapping to 4. You just accessed it in constant time very easily. Okay, so now what are some other functionalities that we have to support? We currently support inserting a new key value pair. We support updating it to be the most recent key value pair. We support getting the most recent key value pair. All of this in O of 1 time. Now, what if I tell you, okay, I want you to retrieve a value from a key. So I want you to retrieve the value from the key B. Right? How do you do that? Well, you just check in your hash table. Is B in the hash table? Yes, it is. What does it point to? It points to a node that holds B and 2. So that's very easy. You just return the value here, which is going to be 2. Okay. Now, if I tell you I want to retrieve the value from the key X, right, which is not in the hash table, well, you just check, and if it's not in the hash table, then you just return the null value. Simple enough. Okay. Now, what if I want you to insert a key value pair where the key already exists in the hash table? So I'll give you a new key value pair that is going to be, let's say, A pointing to 99. Okay. So you're going to look in your hash table. You're going to see that A is already in your hash table. Okay. So because A is already in your hash table, then you're just going to replace the key at value, or you're going to just replace value at key A. So the value right now is a doubly linked list node, right? And the doubly linked list node is A pointing to 1. So all that we have to do is say, this doubly linked list node here, just overwrite the value to be 99. So we'll overwrite this 1 here and make it be 99. Simple enough. And then, of course, the last thing that we do is we update this new key value pair or this overwritten key value pair to be the head of the linked list. So we're going to grab our A pointing to 99. We're going to move it here. We're going to grab our entire cache and hash table and bring it down to give ourselves some space. So A pointing to 99 is going to go to the top. It's now going to become the head of the linked list. As we mentioned earlier, this is an O of 1 operation if you've implemented your doubly linked list correctly. The new tail is going to be B pointing to 2. Again, updating the tail is a fairly trivial task if you've implemented your linked list correctly. We can remove this pointer here, and then we can make this A point all the way to here, A mapping to 99. And again, for the sake of good order, we'll just move it here at the top, and we now have A 99 as the most recent key value pair. So now we've supported all of the different functionalities that we need in constant time, except for evicting the least recently used key value pair. And when do we want to evict? We want to evict when we try to insert a key value pair and the cache is at maximum capacity. Or rather, when we want to insert a new key value pair that doesn't already exist in the cache. So let's say that we want to add the key value pair X, right, which is not in the cache, X mapping to 100. Okay, so we see that the current size of our cache is 4. The maximum capacity of our cache is 4. So we have to evict the least recent key value pair. How do we do that? Very simple. We find the tail of our doubly linked list. The tail is here. So we remove that tail from our doubly linked list. Again, if you've implemented your linked list correctly, this is a pretty trivial operation. So we can just erase this and move our tail up here, right? And we can erase this little pointer here. So we move it, because of course the tail node of the doubly linked list is going to point to the null value at the end to really mark the fact that it's a tail. And then you also want to delete this property from the hash table. So we're going to delete this b here. Delete it. And at this point, well, you redo the exact same thing that we've been doing before. You can add a new property to the hash table, which is going to be x. It's going to point to a doubly linked list node of x mapping to 100. And this is going to be the new head. So we can move the head here and add a couple of pointers connecting the two nodes. And we are done. So, and of course, we didn't touch the current size here because, we were already at maximum capacity and we still are at maximum capacity. So, as you can see, by combining a hash table in the linked list, where each property in the hash table is a key in our LRU cache and points to a node in a doubly linked list that is going to store the key value pair that we're adding, we have been able to implement all of the functionalities of this LRU cache in constant time and also in constant space. Without counting the space of our entire cache, each of those operations themselves use up constant space. You're not doing any sort of gigantic recursive call, or a bunch of recursive calls of some method. You're not storing some additional arrays or variables or stuff like that. So all of your methods are going to run in constant time and constant space. We can actually write it here. Time for all the methods is going to be equal to O of 1. Space for all the methods, again, without counting the totality of the LRU cache. The space complexity for each individual method is going to be O of 1 space at any given time. And that's it. This is how the LRU cache works. If it's not entirely clear right now why it works, I think that it'll be very useful to dive into the code walkthrough, because you'll really see how every single method in the LRU cache is literally just doing, moving pointers, adding properties or deleting properties, but never shifting a bunch of values, right? You're never shifting a bunch of values in an array. You're never iterating through all the values in your hash table in your linked list. You're really just leveraging the sort of the great aspects of both the data structures, a hash table and a linked list or a doubly linked list, and merging them together to take advantage of them. So with all that being said, let's actually dive into the code walkthrough. All right, so we've got our LRU cache class defined. It takes in a single parameter max size, which is going to represent the maximum number of key value pairs that the cache can store at one time before it has to start evicting the least recently used key value pair. And before we dive into the actual code implementation, I want to show you this doubly linked list class that I have here that I'm not going to implement in front of you because it's taken directly from the doubly linked list construction question that we have right here on algoexpert.io. If you haven't checked it out, I would definitely check it out so that you can really understand how this doubly linked list class works. But just so you can understand here, we've got these doubly linked list nodes that have a key, that have a value. These are going to be, the key and values of any given key value pair that we're adding to the cache. All of the doubly linked list nodes have a pointer to the previous node and a pointer to the next node. And then we also have this helper method called remove bindings that kind of is going to help us, move a specific node in the doubly linked list if we want to remove its bindings. And then the doubly linked list class supports two main methods. One of them is removing its tail, and this method is probably going to be called when we evict a node from the cache. And then we've got this method called setHead2, and it takes in a node. This is going to be the method that we call when we are making a new key value pair become the most recently used or accessed key value pair, because we want to store it in the head of the doubly linked list, as we explained in the conceptual overview. So with that, let's actually implement this LRU cache class. The first thing we're going to want to do is add our actual cache, right? The thing that we're going to use to store all of the key value pairs, or all of the doubly linked list nodes and their corresponding keys. So this is just going to be a hash table. So in Python, we can represent it as a dictionary, or in JavaScript, an object. So we'll do self.cache equals an empty dictionary. And then we've got this max size here that's set to the max size parameter that we passed to our LRU cache. And then we can add a couple of other variables here. One of them is going to be the current size of the cache. We definitely want to keep track of the current size. So it'll be initialized to 0. And whenever that current size reaches the maximum size, that's when we know that we have to start evicting stuff if we want to insert more key value pairs. And then finally, we want to keep track of our most recent pairs in the form of a doubly linked list. So we'll have our list of most recent, which is going to be a doubly linked list. And this will be initialized to just an empty doubly linked list. So now we get into the actual kind of crux of the class, the three methods that we want to implement. Insert key value pair, which takes in a key and a value. Get value from key, which takes in a key. And get most recent key. So let's start with insert key value pair. Remember, in the conceptual overview, when we wanted to insert a new key value pair, the first thing that we did is we checked if the key was actually already in the cache. Because if it existed already in the cache, then we just had to replace the value in the cache. Otherwise, we had to do a bit of other logic. Okay, so if key is not in self.cache, and here we're literally just checking, hey, is the key that we're trying to insert in our cache, which is a hash table. So if key is not in self.cache, then we're going to do some stuff, okay? And I'll pass for now because it's going to be a bit more complicated. But otherwise, if the key is in the cache, then all that we have to do is replace the value, or the doubly linked list node, at that key in the cache. And so here we'll probably write a helper method, which is going to be self.replace key at this key that we just passed, and with this new value that we just passed, okay? And I guess before I implement the rest of this insert key value pair method, I'm actually going to implement our replace key method. So replace key is going to take in a key and a value, right? Which we just mentioned, since we wrote it here on line 12. And so first we can do kind of a sanity check, right? If the key is not in our cache, then we've done something wrong, right? If we ever call the replace key method and our key that we just passed isn't in the cache, then something went wrong, and we can probably just raise an exception, throw an error, right? The provided key isn't in the cache. But this will likely never happen. And in the normal cases when it doesn't happen, all we're going to do, right? Because remember, our key is already in the cache and it's pointing to a doubly linked list node that has, if we recall, a key property and a value property. set to the key and the value of that key value pair. So what we can do is, if everything goes well, we'll just say self.cache at the property key. This here is a doubly linked list node. Dot value equals value. So we don't even create a new doubly linked list node. All that we do is we overwrite the value property of the doubly linked list node stored here at the property key in our cache, and we overwrite its value to be the new value. And that's the replace key method. We're done with it. Okay, so now we can go back up to our insert key value pair method. We've taken care of replacing an existing key or an existing key value pair. But if the key is not in our cache, what do we have to do, right? Let's dive into this logic. Well, there are two cases, right? If the key is not in the cache, there are two cases. There's the case where we have to evict a key value pair because we are at the max size, so we can write it here. If self.current size is equal to self.max size, right? If we're ever at a point where our current size is the maximum size, so we are at maximum capacity, then we're going to have to evict the least recently used key value pair. So we're going to make a call to a helper method, self.evict least recent, and we're going to have to write this helper method in a second. But otherwise, right, if we have room in the LRU cache, then all that we have to do here is increment our current size, right? Self.current size is going to be plus or equal to 1, or plus equal to 1. We add a number, add 1 to the current size. And I misspelled current size. And then, of course, this isn't done here. On line 14, we have to say that no matter what, no matter whether our cache is at maximum capacity or not, if the key wasn't in the cache, then we have to add it, right? So we have to do self.cache at property key is going to be equal to a new doubly linked list node with key as the key and value as the value, okay? So just to make sure that we understand here on line 14, we're saying if the key that we passed to our insert key value pair method was not in the cache, right? Regardless of whether we had to evict the least recently used key value pair or not, in which case we incremented the current size, regardless of that, we have to add a new property in our cache, in our hash table, which is going to be the property here, key. And that's going to point to a new doubly linked list node that is going to have our key that we just passed it and our value that we just passed it, okay? And again, if you look at the doubly linked list node class at the bottom, it takes in a key and a value, and it just stores the key in the property key and value in the property value. Now, before we write this evict least recent method, there's something we haven't done yet in this insert key value pair method, right? Remember, when you add a new key value pair, it becomes the most recently used or accessed key value pair. So here at the very end, right, regardless of whether or not the key was in the cache, regardless of whether or not the key was not in the cache, or if it was in the cache, regardless of that, we have to update. So we're going to make a call to update most recent. We're going to have to update the most recent key value pair to be our new key value pair, which is going to be stored at self.cache at property key. And so we're going to write this method as well. Before we write it, let's write the evict least recent method, okay? I don't want to confuse you too much, so let's go a bit slowly and do things one at a time. Let's write the evict least recent method. So evicting the least recent, evict least recent. It doesn't take in any arguments, so we'll just pass in self because we're writing in Python here. And what do we have to do? Well, we have to find the tail of the doubly linked list. Remember from the conceptual overview, the tail of the doubly linked list at all times holds the least recent or least recently used key value pair. So we can just remove that tail, right? We can do self.list of most recent, which is our list here on line 6, which is a doubly linked list, dot remove tail. And that's it, right? If we remove the tail, remember, remove tail is a method here on our doubly linked list class. We've got this remove tail method that literally just removes the tail and updates the node right before the tail to be the new tail. So if we call this remove tail method, it's going to evict our least recently used key value pair, and it's going to update the least recently used key value pair right before that to be the new tail and to be the new least recently used key value pair. I know that sounds confusing, but that's what it's doing. And then, of course, remember, we also have to delete the property, or we also have to delete the key value pair from the hash table. Because remember, just removing the doubly linked list doesn't actually remove the key value pair from the hash table. The hash table still has the property of that key. So here we have to delete, right, the key from our cache. So delete self.cache at, and here you'll notice we're kind of in a little pickle here where we don't actually know what key we just removed, right? We never know what our least recently used key value pair is unless we access it from the tail. So before we actually remove the tail, because now we have no way of actually accessing it anymore or knowing what it is, before we remove the tail, we should actually say key to remove is going to be equal to self.list of most recent dot tail dot key. Remember, a doubly linked list here on line 34 has two properties on it, a head and a tail. So we can always access the head and the tail in constant time. They're defaulted to none, but here our tail is going to point to a doubly linked list node. And so we can say key to remove is the tail of the list of most recent dot key. It is the key of the tail, and now we can delete self.cache at key to remove. And this is the Python way of deleting a property from a hash table, from a dictionary. So that is how we evict the least recent key value pair. If we go back to the insert key value pair method on line 8, we've implemented the eviction portion, we've implemented the replace portion. Then on line 17, we reminded ourselves that we also need to update the most recent key value pair. So let's write this update method. We'll say update most recent, which takes in a node, right? Because remember, on line 17, we passed this update most recent method, we passed it the value of self.cache at property key. What is the value of self.cache at property key? Well, we set it on line 14, and we set it to be a new doubly linked list node of key and a value. So updating the most recent key value pair, we pass in the node that we just added, right? And this is a doubly linked list node, and then all that we have to do is update the head of our doubly linked list to be that node. So self.list of most recent, this is our doubly linked list, right? The list of most recent. And then recall that we have a very handy dandy set head to method that takes in a node. So here we can just say list of most recent dot set head to, and we pass in the node. Again, here the setHead2 method, I kind of abstracted it out of this video because we cover it in the doubly linked list construction question of algoexpert.io. But all that it does is takes an arbitrary node that has to be a doubly linked list node and sets the head of our doubly linked list to be that node. And of course, it updates the current head to no longer be the head, right? So that is our update most recent method. Now, what else do we have to do? Well, we finished inserting a key value pair. Now we have to do get value from key and get most recent key. So get value from key. Remember, if we have to first check if the key is in the cache. If key is not in self.cache, then we can just return none. The prompt told us that if a key is not in the cache, we should just return none or the null value. And otherwise, we can just return self.cache at property key dot value. Because remember, when we access the value of our key in our cache, we're actually accessing a doubly linked list node. And so then we have to access the value property of that doubly linked list node to get the value of this key. Now, if you're paying close attention here, you probably notice that this is incorrect, what we just did, because when we access a key value pair, when we get the value from a key, we actually have to make it the newly most recent key value pair. So before we return the actual value that we're asked to return here, we have to call the update most recent method. So we have to do self.update most recent and pass in self.cache at property key. Luckily for us, we've already implemented this now, so we don't have to re-implement it, but it's important to remember that we have to do this on line 22. And now finally, the get most recent key method on line 25. This is going to be a pretty simple one. It's just going to be accessing the key of the head of the doubly linked list. Remember that the doubly linked list stores at all times the least recently used key value pair in the tail and the most recently used key value pair in the head. So here we can do return self.list of most recent head key. And that's it. We've accessed the most recent key. Because it is the most recent key, we don't have to update it to be the most recent. Like, there's nothing that needs to happen here. And all three of these methods, right, inserting a key value pair, getting a value from a key, and getting the most recent key, all three of these methods are going to run in O of 1 time and O of 1 space. Again, the space complexity is a bit awkward here. Each individual method doesn't really add more space than constant space, and it doesn't use up auxiliary space. The entire LRU cache is going to use a total of O of n space, where n is the max size of the LRU cache, but here we're really dealing with the individual methods. And ultimately, this algorithm, the really important part is the time complexity. This is one of those questions where the space complexity is a bit less important, if I may say so. And so all three of these methods run in O of 1 time and O of 1 space. Now, before I end the video, I just want to kind of re-go through our entire logic so that we're really confident in how this works and why this runs in O of 1 time. So we've got our LRU cache. It has a hash table or a dictionary, an object, whatever you want to call it, as the cache property. It's got its max size, which is the parameter that we passed it. It's got the current size, which we keep track of in the form of a number. It starts out at 0, because when you create the LRU cache, there's nothing in it. And then it's got this list of the most recently used key value pairs, which is just a doubly linked list. Our doubly linked list is this class that has a head and a tail. That's it. And then it's got a bunch of methods like set head to node, remove the tail, and all of that. And every node in the doubly linked list is a doubly linked list node that has a key, a value, and then pointers pointing to the previous value and the next value. Okay? So, inserting a key value pair, the first thing we do is we check if the key is in the cache. If it isn't, then that means that we need to add this key value pair to the cache. So in that case, we need to make sure that our cache is not at max capacity. If the cache is at max capacity, then we evict the least recent key or key value pair. Otherwise, we just increment the current size by 1. Evicting the least recent pair consists of grabbing the key from the tail of our doubly linked list, then removing the tail, and then deleting the property at that key of the tail, right? The tail's key in the cache. So deleting a property is just O of 1 time. Accessing the tail of our doubly linked list, or the key of the tail, is O of 1 time. Removing the tail, if you look at the doubly linked list class, is just O of 1 time, because all you're doing is setting a few pointers from the tail and of the previous and next pointers of the node before the tail and at the tail. So evicting is O of 1 time. So now we go back up. When we're inserting, we either evict or increase the size by 1. Then on line 15, we make sure to add here to store at the property key in the cache a new doubly linked list node with both the key and the value. And by the way, quick caveat here, or quick aside. You've noticed that there are times like when we evicted the key or the key value pair, we needed to know the key of the key value pair just by accessing the doubly linked list node. And that's why we store both the key and the value in the doubly linked list node and not just the value. And I'm sure that if you try to implement this yourself, you'll realize quickly that if you only store the value in the doubly linked list node, there will be a point where you need the key in the doubly linked list node. So that's why we store both. If the key was in the cache, then we just replace the key or the value of that key. Replacing is pretty simple. All we do is we access the doubly linked list node stored in the cache at the property key, grab its value, and overwrite it to be the new value. Okay? And then the last thing that we do when we insert a key value pair is we update the most recent key value pair by passing it the new node or the existing node stored in the cache at property key. Updating the most recent consists of simply calling the setHead2 method by passing it the node. If we look at setHead2, all we're doing is overwriting and moving a bunch of pointers. When we call the removeBindings method on our node, that's also overwriting a bunch of pointers. So this is all O of 1 time. And that's it for inserting a key value pair. Getting a value from a key consists of checking if the key is in the cache. If it's not, just return none. If it is, then you make sure to update the key value pair to be the most recent one, and then you return the value stored in the doubly linked list node at the key property in the cache, and that's going to be O of 1 time, right? Because we said that updating the most recent is O of 1 time. It's just setting the head node to a node, and then accessing a value from a hash table is going to be O of 1. And finally, getting the most recent key is going to just access the head of our doubly linked list and then access the key of that head. And that's going to be O of 1 time. So I hope that this last sort of pass through the entire algorithm really convinced you of the time complexity of all of these methods. Like I said, this is a very famous problem. It's also a difficult one. So definitely don't be hard on yourself if you didn't come up with this solution on the first try, or if you didn't implement it correctly, and perfectly. And I hope this video is helpful. I'll see you in the next one.